All right, so previously we have looked at combustion reactions, and we've talked about why those reactions are exothermic and why they release energy. As those fuels are burned, they react with oxygen and produce carbon dioxide and water. And the difference in the energy of the bonds being broken and the energy of the bonds being formed results in combustion's case with an energy release. And so we've already used the symbols delta H to refer to the energy released by the fuel. And we've looked at the delta T, which should be positive in the case of combustion, as being the increase in kinetic energy of the particles in the surroundings. So this is the energy being gained by the surroundings. So previously we talked about this in kind of a general term, and now a general sense, and now we're actually going to talk about how to measure this energy change experimentally. This technique in chemistry or in physics is referred to as calorimetry, and that means the measurement of calories. Everyone's familiar with calories from food labels, from nutrition labels, and calories are a unit of energy. So it's not the SI unit of energy. We will still use joules and kilojoules, but that's where the term comes from. So we can calculate the energy that is given off by a reaction using water. And we could use other materials too, but water is a good choice. It's readily available, and it's easy for us to arrange near our reaction. So we can calculate the energy that's coming out of a combustion reaction by putting that combustion reaction, shown here as a flame, directly beneath a beaker of water or a container of water. And the idea being that the flame is giving off heat, and a lot of that heat, definitely not all of that heat, but a lot of the heat being given off by the flame will go into this water. And so we're treating the water as though the water is the surroundings, and we have the reaction here. So we're going to have, this is where we have the energy released from the combustion reaction, and then the water is going to be the energy absorbed. And so we've still got the law of conservation of energy. We're assuming that the energy being released by the flame is going into the water. And so here's where we have the negative delta H, and here's where we have the positive delta T. So this is a very simple calorimetry experiment, just a cup of water of some kind held above a flame. And clearly we're going to measure the temperature change of that water. That's going to be one really key piece of data to record in terms of calculating the energy. We also need to know how much water we're heating up. So we need to know the mass of water, the temperature change of the water, and finally we need to know one other value that is called the specific heat capacity of water. Specific heat capacities are different for all different substances, and it has to do with how much energy does it take to warm that material up. And so for water, the value is 4.18 joules per gram per degree Celsius. So what does that mean? That means that for water, you have to put in 4.18 joules of energy to increase the temperature of 1 gram of water by 1 degree Celsius. You can also express it with kilo units, meaning you have to put in 4.18 kilojoules to raise the temperature of a kilogram of water by a degree Celsius. So it has to do with, it's very unique to water, this value. If we put them all together, we get the equation Q equals mc delta T, where in this case, Q, oddly enough, is the energy transferred. In this case, the energy transferred into the water. Now, probably more important than just calculating how much energy was transferred into water by a particular reaction is knowing, well, how much energy was being given out per mole or per gram of that fuel. Remember that comparing things on a per mole basis is a way of talking about it on a per molecule basis, whereas comparing it per gram is about the actual mass of fuel that's being burned. So if we compare the values in this table, I've got methane's values, literature values, and I've got ethane's literature values. We can see that ethane releases more energy per mole, and that's because ethane has more chemical bonds in it that will be broken, and it will also lead to more carbon dioxide being formed and more water being formed. And so the more carbon-oxygen bonds in carbon dioxide. And the more water molecules we form, the more of those really strong bonds we're forming and the more energy we will release. So bigger molecules contain more energy and net will release more energy when they are combusted per molecule. However, big molecules are heavy. So the bigger the molecule gets, the heavier it gets. And that means that actually there's less energy per gram. So if we compare the values down below, we can see that methane, because it's so small and because it's so light, even though it releases less energy per molecule, it actually releases more energy per gram than ethane does. And so that value, that energy per gram, is called the specific energy of a fuel. And it's a really important value because when you're using a fuel, often fuels have to be transported around. And so we care both about how much energy we can get out of it, but how much does that fuel weigh itself? Because it's not really good or practical to carry around very, very heavy fuels. So we can calculate the specific energy if we know the energy that came out of the reaction, that's Q. That's what we calculated on the previous page. And then we divide it by the mass of the fuel. Usually you're looking at a container that has fuel, and so you look at the mass of the container before and after, and so the change in the mass is how you know the mass of the fuel. So that's why there's a delta symbol here. This is the change in mass of the fuel container. And so that change in mass is equal to the mass of our fuel. Okay, so here is a sample exercise to walk through. We've got the mass of the spirit burner before and after burning. The spirit burner is a name for a little glass container with a wick that can burn fuels. Okay, so this is data that we need to figure out the mass of the fuel. Then we have the mass of water, MW, and we have the temperature of the water before and after. That's going to help us get delta T. So when I start off, and I'm going to calculate the change in temperature of the water, 76.5 minus 18, and that gets me 58.5 degrees Celsius as the change in temperature of the water. So that's how much the temperature increased for the water. Then I can use that value to calculate the energy that went into the water. So the mass of the water was 95.84 grams. Specific heat capacity is joules, 4.18 joules per gram per degree Celsius. And that change in temperature was 58.5 degrees Celsius. Now, as we go through it, you can see that the gram unit will cancel. It's on the top and the bottom of that fraction. The degrees Celsius unit will cancel, and we should be left in joules. So if I multiply that out, I get an answer of 23,436 joules. Usually we end up wanting these values in kilojoules, and 23,000 is kind of a big number. So I'm going to divide by 1,000 and get myself down to 23.4 kilojoules as my Q value. This is the energy that went into the water based on this data. I also rounded off, so I only have 3 digits, and that's because you can see in my calculations, I had a value that had 4 digits, I had one that had 3 digits, and I had one that had 3 digits. And so there's a system for rounding off, which is called significant figures, and usually when multiplying and dividing, you can look at which of your numbers has the fewest digits, the fewest significant digits, and round based on that. So I'm using 3 in my answer because a couple of my values only had 3 digits. Okay, calculate the change in mass. The change in mass is the difference in these two values. That's 1.34 grams. That's the change in mass of the fuel. And so finally, to calculate specific energy, we are just going to calculate the energy divided by the mass of fuel it took to give us that energy. And so that gives me 17.5 kilojoules per gram. So if we know the energy that's being released and we know the mass of fuel that we burned, we can get the energy per gram for that fuel. Okay, Okay, the final thing that you'll really be asked to calculate, or nearly the final thing for now, is a percent error value. Percentage error is a way of quantifying how inaccurate your value is. And in order to calculate that, you need to know what the true value is. In science, we often call the true value or the accepted value for something the literature value, because we find it in the literature. And so the literature value for this fuel, the specific energy, was 22.7 kilojoules per gram. So if I want to quantify how far off I was with my 17.5, I'm going to use this equation for percent error. So the literature value was 22.7 and my value was 17.5. So I'm going to subtract to find out how far apart they were, what the difference was. And then I'm going to try to express that as a percentage. So what percent is the error out of the true value? So the actual error, I was 5.2 off, but out of 22.7, you can see maybe that's around 25%. When I calculate that, I get a percent error of 22.9%, which I think it's okay to round off to about 23% error. So this is our percent error in this example. So it's a good thing to do at the end of a lab if you have a literature value to compare to, is to quantify the amount of error or the amount of inaccuracy you have. How far off were you from a literature value?